Today's episode of the Markey Podcast is a talk that I gave to a group of undergraduates at Cal Poly San Luis Obispo in October of 2019. We were invited by Professor Branner of the Electrical Engineering Department to speak about MMIC mixer technology and how it's changed over the years. Because this talk was geared towards a seminar of undergraduates, I decided to make the content more of an introduction to RF and microwave technology, and I think it's a really great place to start for anybody interested in learning more about the field but doesn't quite know all the details yet. If you enjoyed this talk and would like to invite myself or Doug or anyone else from the Markey team to speak about Markey's technology at a future event, please don't hesitate to contact us at www.markeymicrowave.com.
Chris Markey from Markey Microwave. How long has that company been around now?
Well, it's my first slide, so I'll just put it up there.
Okay. We're kind of in the pre-meeting.
Yeah, no, I got you, but
yeah.
they can read through it.
Yeah.
We formed in '91. My dad formed it with my mom. My dad had been, I wasn't going to get too far into his background, but I should describe it because it's interesting. My dad's like a very famous mixer designer, and he got his start in 1971 coming out of Berkeley, and 20 years into his career, he was about 50 years old, he decided he would form his own company. And so they formed in '91, right at the end of the Cold War, which was a terrible time to start a microwave company.
Peace penalty, right?
Peace dividend, yeah. And but they made it work. Yeah.
So was he able to kind of just have enough money saved up to kind of just do it from scratch then, or did he have to get investors?
No investors.
No investors?
Yeah, so it was all bootstrapped.
Yeah, please, yeah.
Yeah, it's one of those Silicon Valley immigrant stories that you hear about. He's originally from Hungary. He came to the U.S. and he was like, I think 20 years old, and was immediately drafted into Vietnam, and then was discharged. Oh yeah, because you can. I think if they're like, if you're gonna stay, you're gonna have to fight. Yeah.
Oh, wow.
He never got deployed actually, so he dodged that bullet literally, and he eventually went to Berkeley on the GI Bill, and decided to go into fields and waves as a specialty. And his argument, which is really good advice for all of you, and I strongly recommend you do this. He went into fields and waves for two reasons. In the around late 60s in Berkeley, it was an interesting time. That was when like the digital revolution was like beginning, and there was Fairchild, and Intel wasn't even a thing yet, but I think CMOS was obviously going to be the winner of the day at that point. And those classes were packed, and they were all taught by TAs. And my dad was like, I'm not going to do that. I'm going to go into the class with like 5 grad students, and everybody says it's a dead field. Because he figured he could get a job if he went into the specialty with 5 people instead of 250 in the big lecture hall. And that advice is really important. And like always remember that don't be like the person next to you in terms of your specialty. Learn something unique. It's kind of like anybody a jazz fan? You listen to jazz or music kind of person. It's like the whole thing about jazz is to find your own voice. Like you play like you. I think there was like a Miles Davis quote I heard. It's the hardest thing I ever did was figure out how to play like me, or some kind of paraphrase like that. But that's really important in electronics, especially. You can go become a CMOS designer at a giant company, or you can choose a different path. And there's obvious benefits to doing something that's very popular, but there are a lot of benefits if you have an actual specialty where you know something other people don't know. And for the simplest reason possible, you can't be fired. If you know something in your firm that no other engineer knows, it's job security. And my dad used that to to a high level of success in the first 20 years of his career, and he decided to start his own firm right as the Cold War ended, and that pretty much sent a wildfire through the microwave industry, and it was ironically a very good time to start a company because all the competitors were weakened, and since he had no mouths to feed besides his own, he could, be very aggressive and go after business, and there wasn't like the baggage of laying people off or anything. And so by the 1995, 96, they were doing really well and growing at that point.
Yeah, I always admire somebody who can do something like that.
Yeah.
It's so easy to be the person who's paid a regular salary and go home, but when you put yourself out there, and then especially when you start having employees, and you know that these employees are depending on your success for their success, and that's a big weight on people's shoulders when they do something like that. So very amazing.
Yeah, real life will get in the way of your engineering career. So like that revelation, that realization, as you go through. I'm 39. I've been doing engineering essentially since I was 20, and the hardest thing, and I tell this to the rising engineers, the hardest thing you'll deal with is not the technical stuff. Everything you're learning is fine. Like, it's easy, really. Like, compared to what dealing with like an employee of yours, or like let's say you're a supervisor to somebody and their wife is sick with like a serious illness, or they can't come in because their kid's sick. They gotta, or for whatever reason. Those are by far the hardest things to deal with. You have to know your technical chops, but there's a whole side of your career that you don't even realize will have to develop eventually.
Okay, well, that was a great pre-work discussion there. So I think I will officially have the starting bell here for the weekly seminar. And today we're so happy to have Chris Markey from Markey Microwave in Morgan Hill visiting us today. Drove down on his great Tesla. It's kind of fun to be inside a Tesla again.
The cliche CEO driving a Tesla in Silicon Valley. Yeah, it's true.
So we had a chance to discuss all our fun things in graduate school and some connections we had perhaps, and so just a wealth of knowledge here. So I just wanted to give a round of applause for our speaker today, Chris Markey.
Thanks for having me. We have enjoyed meeting a lot of former graduates of this school. We employ several of them, and certainly one reason I'm here is to try to recruit to some extent. So if you want to talk to me later, please do so. But today I want to talk primarily about the work I've done since I started at Markey. So the timeline of the company, as we kind of discussed in the preamble, is we were formed in 1991. I was 11 years old at the time, and my parents' primary goal was just to pay themselves and feed themselves and put their kids through school. It was a very, very minimalist mindset. They just wanted to survive, and they did quite well. By the 2000s, they were doing very well, and the military spending had started to come back, and that's primarily what our business is geared towards, is defense and test and measurement, which I'll show you in a second. I started going to grad school in 2002, and originally I was studying photonics, so that's where we have a shared past. By the time I graduated in 2007, I decided I wanted to go work with my dad, and the reason I wanted to work with my dad was that he was an entrepreneur and a designer, and both of those things really appealed to me. I liked the idea of coming up with new concepts and new ideas that I hadn't seen before, but then instead of publishing them for the IEEE, making money from them and selling them to people who could use them. I always felt like people ask me a lot, what's the most rewarding thing about my job, and by far the most rewarding thing is getting the first sale. It's not even like, what the revenue is. It's that recognition that what you did helped somebody and really made a difference. And everything I'm going to show you today has been adopted by our customers. In many ways, I look at them as my little babies. So, and you guys are in a very unique position. I wouldn't even show you pictures like this to my own customers. I'm only showing this to you because I pretty sure you won't know what is going on. So yeah, this will self-destruct, this message. So no cell phones. The resolution's not good enough anyway. So we've had a lot of success since I started in 2007. We're about 5 times bigger than we were when I started. And the main contribution I've made to the company is that we are now in the semiconductor industry, as opposed to when we started, when we were just doing what's called hybrid manufacturing, which is handmade products that are soldered together, cut, pasted, glued, tuned, and shipped out the door. Now we do the high-tech thing. It's we fabricate on wafer, and robots do the pick and place, and then everything gets cured in parallel in an oven. And it's a different manufacturing mindset. It's a different business model. We do it all under one house or under one roof. And so everything I'm going to show you today is centered around the semiconductor portion of the products. Okay, so the jumping off point is I feel like it's important to describe to you a fact of the semiconductor industry, which is that most of the semiconductor world is centered around silicon. It's why it's the Silicon Valley and not the gallium arsenide valley or the indium phosphide valley. Silicon has a lot of special properties, which I'm sure your professors will teach you about. And it's a beautiful thing. It makes the world go around. Moore's Law, you've heard of it. It's a thing. It's important. I have nothing to do with that. All of the semiconductors that we do at Markey Microwave are what's called compound semiconductors. Who here has heard of that word? Compound semiconductor. Okay. So
take my class, the
yeah.
29 winter quarter. You'll know a lot about some gallium arsenide at that time.
So compound semiconductors are single-digit percentages of the entire semiconductor industry. So it wouldn't shock me if 99% of the industry was silicon and 1% was compound semi. However, that doesn't mean it's irrelevant. It's super important. What can it do? Well, it's really important in optoelectronics. You can make lasers with them. You can make photodetectors with them because of what's called direct band gap. So I'm told you guys don't know what band gaps are, but you'll learn about them hopefully. Direct band gaps are important, and silicon doesn't have it. So it makes it not be very good for doing photon electron interactions. What else? What else do we do with gallium arsenide? We make amplifiers. Every one of your cell phones has a gallium arsenide power amplifier inside of it. You might not know that. It's probably designed by one of a few people. It could be Qorvo. It could be Skyworks. It could be, I think those are the 2 big dogs. But those companies only build their gas products or they only build their PAs on gallium arsenide. Why? Pretty much power and efficiency. That's the name of the game. Your phone heats up when you use it for a while. That's the PA heating up. And that's the enemy of your battery, right? So there is a little bit of gallium arsenide in your pocket right now. What else do you do with it? You make radars. So all of the phase array radars that the US military, well, every military has, the US military is extremely good at it. There are these giant hundreds of elements, if not thousands of element arrays that can do steerable antennas. And that technology is usually these days based on gallium nitride, which is a very important upcoming semiconductor. So the point I'm trying to make is that even though silicon is the most important technology out there, it was the backbone of Intel and the backbone of Apple and Qualcomm and Samsung. There's this whole world out there of exotic semis, and there's a lot of fun engineering to be had there. And I strongly recommend you at least consider it when you're taking your courses. Like, I'm not just trying to pitch his course, but like you should learn about these things. Because, like I said, swim upstream, swim away from where all the people are going to. Make yourself unique, even in undergrad. Today I will only be talking about exotic semis, and specifically gallium arsenide. So that means, almost by definition, I'll be talking about analog circuits that are niche-y. They're pretty custom. They only do single function. What I mean by single function is that it's very common, well, it's pretty much understood that when you make a silicon chip, that there's going to be all this processing on it. You know, If it's an RF front end, like an RF receiver, it'll have amplifiers, and it'll have switches, and it'll have all these other things in there. It might even have an analog to digital converter integrated or something like that. So that you'll have the analog and the digital possibly on the same chip, or at least very well integrated. In my field, we don't do that at all. We make like one thing, like an amplifier. The amplifier in your pocket is an amplifier. I don't think there's anything else on that die. And why do we do that? Performance. It's just you can't make it as good if you add the other stuff there. And that's where we come in, and that's our specialty at Markey Microwave. So these are the customers that we primarily cater to. And there are some of the biggest companies in the world that we even will sell to, the likes of a Google or a Facebook even, because they are involved in RF and microwave development for their own needs. But our two biggest customer bases will be test and measurement. So that's Keysight, Anritsu, Rohde & Schwartz. Who else do I have up there? Tektronix. You've probably heard of most of these people. And then there's the defense side. So there's the Lockheed Martins of the world and the Northrop Grummans of the world. They all have the same basic problem, is that they don't have a high volume compared to Qualcomm or Apple. Like Apple's selling things with millions of units or tens or hundreds of millions of units. These customers that we cater to want hundreds to maybe thousands of units. And so the economics of development completely flip around. The other thing that test and measurement and military share is they will pay extra money for the last dB of performance. If you're dealing in a consumer end product, you often have to make a trade-off. Like, oh, well, because I have to meet this power dissipation requirement because it's on battery life, I can't do the extra cool thing that I want to do. But if you're selling to Keysight, they don't necessarily care about that. They want like the Lamborghini product, and so that's what we try to do. So I'm going to show you some Lamborghinis. The Lamborghinis that I'm going to show you today are in what's called the mixer technology that we sell. So who has heard of a mixer? Okay, good. Who knows what a mixer does? What does it do?
Mixes two frequencies together.
All right, good. Mixes two frequencies together to create what?
Like a weird mixture of voltage.
What is that mathematical relationship?
It's like cosines and sines.
Well, no, but okay, so if I come in with frequency 1 and frequency 2, what do I get out? I do get that. What am I trying to get out? Let's put it that way. I'm trying to get out either the sum or the difference. And then what do I not want? Everything else. And that's really hard to do. So our specialty is making mixers that give you the thing you want and eliminate the things you don't want. The things you don't want are often called intermodulation distortion. You will probably learn that in some mandatory course. It's associated with unwanted nonlinearity in the devices, so you'll have to do some nasty math and Taylor series and horrible things like that. But eventually you'll not have to do it by hand because computers will do it for you. So that's nice. We specialize in that, so we specialize in making very clean mixers. Very clean mixers are very important because if you're dealing with like a radar and you don't want artifacts in your receiver, the mixer section tends to be the dirtiest thing on the receiver. And so you don't want to see, like, let's say, a false positive. Like, we see a blip. Oh, no, that was just the artifact of the mixer. That's a very common type problem. In fact, the US military uses that to their strong advantage because you can spoof people. So you can make it look like you're coming from a different direction by jamming people and doing all kinds of weird things. We don't deal with that. That's, if you want to do that, go work at Raytheon. Receiver problems are universally the same. It's all about dynamic range. So if you're testing on a Keysight spectrum analyzer, do you have those here?
Yep.
So Keysight spectrum analyzer, in fact, your professor has developed them in his previous life at Keysight, or Hewlett-Packard at the time. Dynamic range is the key. So the cleanliness of your receive chain matters. So that's what we do. Roughly half of our business is in that kind of product. And that is why I've put most of my time at the company into developing the chip level versions of the old school stuff my dad did. Okay, so I'm going to give you a little bit of knowledge. Well, no, this should be review actually, I think, for most of you. I'm going to be talking about what's called a diode-based semiconductor process. What does that mean? Well, it pretty much means that it's a semiconductor wafer with diodes on it that I get to design to my heart's content. You may say, well, how does that differ from other processes? And I would say that I'm already in an exotic platform, which is a compound semiconductor. Like I said, it's maybe 1% of the entire global semiconductor industry. And within that, I'm talking about 1% of the 1%. So this is like the billionaire class of semiconductor processes. Very few people actually work on these processes. Most people work on the processes that develop amplifiers in your phone. So your phone is typically an HBT, a heterojunction bipolar transistor-based amplifier on gallium arsenide. HBT amps are great for making, or HBT transistors are great for making amps. Diodes are great for making mixers. And so the diodes I'm going to show you today are very high performance. They're much better than what you would get on a traditional process. So what does a diode do? It's basically a current valve. You can think of it that way. You put positive voltage on it, it conducts. If you put negative voltage on it, it doesn't conduct until it eventually dies. There's a lot of different types of diodes. So, I do want to point out one quick thing for the physics nerds here. What makes gallium arsenide diodes better than silicon diodes? Because somebody could say, well, why not just do silicon products? And there's a really simple answer, is that, and this is, I think, is this always true? I think it's almost always true. Compound semiconductors tend to have much better electron mobility. Is that always true? I think it is.
For everyone we care about.
Yeah, for everything you care about. Gallium arsenide's fast, indium phosphide is fast, gallium nitride is fast. Those are the big three dogs. And electron mobility relates to the resistivity of the semiconductor. So if you improve the electron mobility, you reduce the resistance of that current path. And that's really good for me because it means that I don't take losses in the mixers that I don't want. Gallium arsenide is about 5 times higher mobility than silicon. And that's why we like it for diodes. Okay, so there are 3 main types of diodes that are used heavily in the RF and microwave space. I've used the term actually several times now, haven't defined it. Are people familiar with what I mean when I say RF and microwave? Do I need to define? Okay, higher frequency. What I mean specifically for like this context is anything from hundreds of megahertz through 110 gigahertz. So sometimes you say RF through millimeter wave. We build products all the way through 100 plus. When people build these products, these analog circuits for these frequency ranges, the 3 big important diodes are PIN diodes, Schottky diodes, and PN junction diodes. I think all of you will have to learn the basic semiconductor physics in your coursework. I'm not going to get into it right now because I'll actually fail the exam because it's been so long. But I'll tell you what the applications are because the applications are really important. So in Schottky diodes are known to be very fast. They're majority carrier devices, which you'll learn about, and they can be switched on and off very quickly. So they can respond to 100 gigahertz signals. Very important if you're trying to switch a mixer on at 100 gigahertz, right? If the switch can't turn on and off quickly, you won't get mixing in the first place. So we like Schottky diodes. Other things that Schottkys are used for are in detectors, so just straight up power detection, and it's the same basic principle. Have you heard of rectification? Everybody's done a rectifier, right? So you put a signal through a diode, and then you get that like half sine wave thing, and you put it through a RC network, and then you get that like RC exponential decay thing, and you say, oh, I made DC. Yeah, okay, well that's a rectifier, and that's basically what power detectors do. And then there's this other really cool thing called a nonlinear transmission line, which I won't be talking about today. Maybe we'll come back some other time and talk about those. PIN diodes. PIN diodes are super important, both in optoelectronics and in RF. In RF, the main application is for switching. So if you come into a common node and you want to switch to the left port or the right port, a PIN diode is a good way to do it. It's very low loss, and it's very good linearity. I may or may not have to describe linearity later, but the cool thing about a pin diode is that it looks kind of like a tunable resistor. So the reason you use it for a switch is it can go from like close to 0 ohms or to like a mega ohm of resistance to the signal. And that's really useful. It also means you can do like analog things, like I can actually continuously tune it. So I can do, instead of cutting off all the power, let's say I cut half the power. That's called an attenuator, or maybe a quarter of the power. And then the final one is called a varactor. A varactor is a PN junction in reverse bias. So when all these diodes that I'm describing, by the way, the basic physics are almost all the same equations. It's just there's some small differences in I guess, the math. All these diodes in reverse bias have a tunable depletion region. You guys know what depletion regions are? Okay, so when you put a negative current or negative voltage on the diode, you change the depletion width. And that's like a parallel plate capacitor, so you can change the capacitance. Tuning capacitance is really useful for a lot of things. Primarily, you can tune LC resonators, so you can tune like, I think you can use them for like tuning antennas. You can tune filters. You can do all kinds of fun stuff. So those are the big three. We are only going to talk about Schottky diodes now. Okay, so Schottky diodes. You can buy them a lot of different ways. And this slide, I think, is a perfect cross-section of our company. We make products that are what's called hybrid, and we make products that are what's called MMIC-based or integrated semiconductor. Have you guys heard the word MMIC before? No, okay. So have you heard the word RFIC? Okay, so in the parlance of what I'm talking about, typically, and I don't even know if this is a universal truth, but I think it's true by slang terms at least, RFICs are RF circuits, RF integrated circuits, RFIC, that are typically built on silicon germanium or some kind of silicon process. And they're typically going to be multifunction. So they'll have like amplification with some other thing there. Maybe an amplifier with a mixer, with maybe also another amplifier, or maybe even some filtering, or maybe a multiplier, or maybe a divider. So there's all these things that they'll do. That's typically what's called an RFIC. A MMIC stands for Microwave Monolithic Integrated Circuit. MMIC. The MMIC technology was originally developed, I believe, by DARPA in the 80s, and it was a very important defense technology for all the reasons I have already explained regarding things like radar. And MMIC, when people say MMIC, they specifically mean, or they're pretty much always implying that it's a compound semiconductor with a single function on it. So I'm going to use that word a lot, so just in case we're like, he didn't define what MMIC was. MMICs are the thing on the right. You can buy Schottky diodes from these big companies like Skyworks, and you can buy them a lot of different ways. They come in a lot of different flavors, different packages. They're very useful if you're doing like a student project where you want to build a down converter, and you just buy like a simple diode from Skyworks and it'll work to gigahertz, and you've passed your course. And that was how my dad built his mixers. So the mixers that my dad, and this mixer right here, this is one of those pictures that like I would have to kill you if you took it. That's our most important, what's called hybrid mixer. Hybrid mixers are, well, okay, now I also have to define something else. I've defined MMIC, which is a monolithic IC, microwave monolithic IC. I have to define hybrid. Hybrid simply means it's a component, a microwave component, that has been usually hand-built and is a composite of many different materials that have been put together typically through either like silver epoxy or solder or something like that. It's a hybrid assembly of many different technologies put together. Up until really the 90s, but you know, I guess if DARPA was working on it in the 80s, it was probably widely available by the 90s. Before like 1980, almost everything was a hybrid in the microwave space. There weren't that many chips like mixer chips and amplifier chips. Like they would be a transistor that you would wire bond together and do impedance matching on this breadboard PCB, and then you would like tune it by hand and make an amplifier. That's the old school way. And so my dad came up in that era. And so everything that we did up until I arrived, and it was about 5 years after I arrived that we started doing this. So up until 2013, we didn't even do this. We only did hybrids. So hybrids take a diode that has already been packaged by somebody else, and we package it within the package. Can anybody think of problems with doing that? And there's a lot of them. So shoot. What do you think's problematic about building something that way? Bigger. Yep. Definitely that's a huge problem. What else? It can have more interference because the fields usually radiate a little bit more. That's true. Yep.
You're adding like capacitance and inductance when you plug it up.
That's a huge problem. So there's this idea, this concept in packaging called parasitics. And when you package a diode in another thing, you're adding size, physical size, to the structure. And if you become an RF person, or especially if you become a microwave person, like over 10 gigahertz is where I'd say, okay, now you're becoming a real bona fide microwave engineer. Below 6 gigahertz is child's play. Above 10, you actually have to be like, strong. What happens is that the interconnections, the physical solder joints, become an appreciable percentage of the wavelength of the signal that's traveling through the device. So let me say that again, because that's a really important thing. This is the distinguishing factor in what makes something microwave versus what makes something low frequency. If the structure is close to the wavelength, and I would say close is within an order of magnitude. So if it's within 10% of the wavelength, you're going to see weird things start to happen. And the problem is, like this gentleman has said, as you go to higher frequency, that issue becomes worse and worse because at higher frequency, wavelength what? Is lower. Wavelength is shorter at higher frequency. So that means that something that was 10% is now like 30% of the wavelength. And there's this magical thing that happens around quarter waves. And there's another magical thing that happens at half waves that can be really nasty. And so the thing stops working. Okay. So when you make things by hand, there's a physical limit to the human hand. And I would say that the rule of thumb that I would give is an amateur can make something to 6 or 10 gigahertz. A pro can make something to 20 or 26 gigahertz. An elite pro, an all-star, can make something to 40 or 50, and then after that, you're guessing. So we have products that are made by hand that go to 40 or 50 or 60 gigahertz, but the consistency is super bad. You're at the mercy of like exactly the size of the solder joint. It becomes a nightmare. It's like really difficult to produce. So scale is the outcropping of this. Is like it's really hard to make a lot of these. And so what does that do? It keeps the price super high. So if I have a customer who says, that's great, I want like 1,000 of these, I'll actually say you can't buy that. And I say, why? I'm like, because the price is still going to be $1,000 each. And they say, why can't you scale it? Can't you like make, give me a deal? I'm like, it costs me the same to make the first piece as the 1,000th piece because I'm going to be throwing away a whole bunch of them with bad yield. So it's a problem. This is why I got into semiconductors, is that I was tired of watching the pain of people supporting products that were made by hand. And so you can see the beauty. Now, I consider this picture, this hybrid assembly, beautiful. And the physical size of this is about 1/4 of an inch by 1/4 of an inch. So it's blown up here, so it looks like, that can't be too hard. It's crazy small, and it's made by hand. It takes about an hour to build each one of these. It's like making a piece of jewelry. And we ship something like 20,000 of those a year. So there's 20,000 work hours to ship those. It's 10 full-time jobs. And that's all they do all day, is that. And it takes you about at least 10 years of solder assembly training to be able to build that. So that people say manufacturing's dead in Silicon Valley, and the answer is, well, not where we are. Not in our building. We're still making these in the US up the street. it's also like $150 each, so like, it's not cheap. Okay, so the MMIC side, there's obvious advantages. There's scale. I can make it once I own the mask, I can make an infinite number of them, quasi-infinite number. I can, and this is the beautiful thing from a design perspective, I can tailor the diode to exactly what I need. So when I buy something from Skyworks, I have a limited selection of values for like the capacitance of the diode. If I design it on a wafer, I can dial that capacitance into within about 5%. And that makes a big difference when you're trying to get those last little perfect conversion efficiencies or something like that. Okay, so now let's talk about mixers. So I just mentioned that we can make a bunch of different types of, or we can tailor the diode to what we want. What's really cool, and the thing that is necessary when you do mixers, is that you have to have a low barrier or a low power version and a high power version. So low power versions are necessary for power efficiency, as you would imagine. And then the high power ones are necessary for what's called high dynamic range or high linearity. When we got involved in the semiconductor space, I started working with the foundry to help develop custom devices because they didn't actually have devices that worked at low power before about 2013. Or sorry, before about 2015. So the devices that we worked with them to, well, I can't take credit for the design of the device. This is all GCS, who's based in Torrance. When I first met them, they only had the green one, and typically you measure diodes based on their forward voltage. That's a very common way to quote it, and that forward voltage at 1 milliamp. So at 1 milliamp, the standard gallium arsenide diode has about 0.7 volts. And I said, well, I need something more like 0.25 because that would be equivalent to a low power mixer. And so what they did is they went back into their lab and they dialed up a new recipe. And what they did is they changed what's called the epitaxial layer where the metal and the semiconductor touch. And Schottky junctions are, the quality of the Schottky junction depends on a lot of chemistry that I don't even understand, to be honest. And it's very like trade secret stuff, so they won't even tell you how they did it. We co-published a paper, and they still wouldn't tell me how they did it. They just said, we engineered the epitaxy. I think they dope it, and they grow different materials on there, and they sort of like engineer it to have a slightly different band gap. But I don't know for sure. But anyway, all they do is they take the start wafer and they grow a slightly different layer on top of it than the original. And you end up with these different curves. So the different curves relate to 4 completely different recipes. There's what we call super low barrier, which turns on around 0.25. Then they had what they call low barrier, which is like what did they say, 0.5, then 0.7, then 0.86. And because it's gallium arsenide and it has very high carrier mobility, it ends up with a very high RC time constant. So the capacitance of the junction times the resistance of that channel is a time constant. That time constant relates to how quickly you can charge and discharge, how quickly you can take charge out of that junction. The faster you can take charge out of that junction, the faster you can switch the device. So if you want to make high frequency mixers, that's really important. And that RC time constant translates into terahertz, which is a pretty impressive thing to say. So they say, this is our terahertz process. You can't achieve that kind of speed in a different type of technology. You have to pretty much make the diode specifically to be as good as you possibly can. Because if you were to, and there's caveats to what I'm saying, but if you were to say to a foundry like GCS or Win Semi, who's in Taiwan, said, I want this diode, but I also want an HBT to make an amplifier. I want to integrate an amplifier with a mixer. They'll say you probably can't do that because you can't actually create the structure physically. So you're at a fork in the road. You're either going to have this or that, but not both. So that's why it's a specialty process. Mixers, we've already discussed what a mixer does. A mixer takes in 2 frequencies and creates a third out, which is ideally only either the sum or the difference frequency. You get a lot of other garbage out. I'm not going to describe the physical mechanism of it because I don't think it would be very helpful to you at this point. Let me just say one thing. Mixers have 3 ports. The large signal port, which is the one that is designed to turn on and off the diodes, is called the local oscillator. You can think of it as like the bias on an amplifier. Amplifiers are active devices. They require DC power and current to create amplification. Mixers are the same way, except for the bias is an LO signal switching on and off. And what it's doing is it's chopping the diodes to go from conducting to non-conducting. Then we pass another signal through it, and it's a small signal, so by design you want it to not flip the diodes back and forth. And as long as it's not flipping the diodes back and forth and competing for the conductance of that channel, you get a very linear, what's called a very linear mixing. And it's almost like strobing it. So the diode is like an on-off light, and then you just see like pieces of this small signal as it travels in time. The Fourier, you guys have all taken Fourier analysis courses? Fourier series, Fourier transform, okay. So the Fourier series, if you take the Fourier series of a chopped signal, you will see the sum frequency, the difference frequency, and the odd LO by 1 RF. In real life, you get a lot more than that. But I'm just trying to give you a little bit of the theory. So that's how these things work physically. There's a time domain plot. Hopefully your professors will teach you this one day. Okay. So there are a lot of very complex circuits that mixers can be built using. The classic circuit that people talk about typically in your coursework, and then if you open up any mixer textbook or you look it up on Wikipedia, you're probably going to see the schematic in the upper left. I call that a center tapped double balanced mixer. And it's even drawn with like low frequency flux coupled transformers. We don't actually do it that way. But there are ways to convert those structures to an IC. And so that's what I'm showing here. Now, this isn't my chip. This is a competitor's chip. And when I was creating this talk, I actually had a good laugh privately because I always mock my competitors for making very simple circuits. And the reason I mock them is that almost all of the performance advantage that my product would have versus a competitor is that I'm not using the same circuits they use. And so it was funny to me when I was like, what's the most basic thing I can do? And then I looked up and they do exactly the most basic thing you can do. And so that's why I'm showing you exactly the same structure. So there's the ground point, there's the IF extraction right out of the center tap of this spiral transformer. On the left side there's the LO, on the right side there's the RF input, and then on the bottom there's the IF. So there you have it. There, you can reverse engineer this. This is off Google Images. You can now make a company. They sell theirs for like 25 bucks. So if you can find a market and you have about 75 grand to burn on a wafer, you're in business. Quit school. So we don't do that. And the reason we don't do that was that you have to think about the timeline that I described originally. My dad started in '91. By that point, there were these types of mixers available on the market. So my dad was always competing with this stuff, but he was building it the hand-built way. So what he had to do is he had to come up with all these really complex circuits that could do extra things to provide additional performance that wasn't available with this kind of like, simple kindergarten design that I'm showing up there. And so that's what he did, is he proceeded to design all these new types of circuits. And I'm just showing you a handful of them right here. The A and B and C are in the class what we call double balanced mixers. And they're the same in the sense that they're like the classic design. They just have slightly different passive structures around it. Now, the most important thing I could tell you about becoming, if you want to become a mixer designer, and this is what my dad told me many, many years ago when I was at his feet. He says, son, if you want to be good at mixers, you got to know how to do passives. You have to know how to do everything else around the diode, because that's actually what makes the mixer good. So I've spent all of my time in this talk telling you about diodes. And I'm like, oh, well, the Schottky diode's got to be fast, and it's got to be this, and gallium arsenide's better than silicon, and all these things. Actually, that's a lie. You can make a good mixer with a bad diode. if you know how to make a good mixer. So it's the structure around the diode, because that's actually how you get the signal in. It's how you extract the signal. It's how you improve the linearity. It's how you improve the isolation. All of these things are really important. A mixer data sheet has about 10 different metrics that are important. And so to get all of those is like a game of whack-a-mole. And so the reason that you go to the higher complexity circuit is that it enables you to knock out more of those 10 important metrics. If you only do, so if you do that simple one in the upper left-hand corner, you'll maybe get 5 of the 10. And so and your application will be maybe satisfied, maybe not. It won't be satisfied for my customers. Keysight's not going to accept that. They're going to say, well, that isolation sucks, or that IP3 is no good. So that's when you start inventing these new circuits, because mixer technology is a circuit technology, not a diode technology. Okay, so the one in the upper right is actually what my dad was really famous for. He is probably the world expert in triple balanced mixers. And what it is you can think of it as 2 double balanced mixers driven in parallel, but out of phase with each other. And when you do that, it takes what's called the IF current, and it makes it differential IF current. That requires an extra transformer on the IF line if you want to convert that differential signal into a single-ended signal. So I'm kind of talking fast, but I'm trying to explain, I guess, the importance of understanding that the evolution of these circuits can get out of hand very fast, and they become very complicated very quickly. And even drawing them in 2D is hard. So you can imagine then if you have to lay them out on a semiconductor, you're going to have some layout issues, because these lines are crossing and they're going very long distances. And what do we say about parasitics? When the lines become similar to the wavelength, things stop looking so good. Sometimes people call it the lumped element equivalent versus the distributed element equivalent. So what did I do? If I did anything, my contribution to the field is that I took my dad's circuits and I ported them over to MMIC. And so I'm going to show you some of those now. So in order to do that, I mentioned that you have to know passive products or passive circuits pretty well. The specific thing you have to know how to do well is what's called a balun. So a balun stands for balanced to unbalanced transformer. What it does is it takes a single-ended signal and it creates differential, or it does the opposite. And because it's a passive reciprocal network, it works in both directions, perfectly happy. In fact, our company sells baluns by themselves, and it's a major product line for us. Why do we do that? Well, all of the important high-frequency, high-speed, analog to digital converters on the market, the ones made by companies like Analog Devices. Have you guys heard of Analog Devices? ADI. Huge, or Texas Instruments. Yeah, Texas Instruments is also that guy has a TI shirt. Yeah, so TI and ADI are like rivals in the ADC space. They're both our customer for baluns. So they like to buy the balun and put it before the ADC, because ADCs like to take in a differential signal. But most signals coming from the world are traveling down single-ended transmission lines. An example of a single-ended transmission line is coax. So coax is a ground shield, and then the hot lead in the middle. You have to convert that to a differential before you sample, or else you take a penalty in the sampling. And what's up?
Yeah, are baluns bidirectional? Do they go single to differential?
Yes, they're reciprocal, assuming it's passive. Yep. So you can also use them on DACs. So you can do, a DAC will come out with a differential, and then you might want single, so you put a balun there, or the opposite direction. You might want it differential out, so you flip it around. My expertise is in balun design. So this particular slide just shows you all the different types of baluns there are, and there's like a ton of them. Something to take away from this talk, have you guys heard of ferrite before? Ferrite is a magnetic material. If you take a magnetic material and you put it around a coupled line structure like a bifilar twisted pair, or you put it around coaxial cable, or you put it around pretty much anything, the higher mu constant, mu is the magnetic permeability of that material, will enhance the coupling between those two pieces of metal. And when you do that, something magical happens in the transformer where it pulls the low end all the way down close to DC. So if you want to make something super broadband like a mixer, it actually requires ferrite. Otherwise, you're going to be dealing with coupling that only exists in the gigahertz domain. This is the sole reason why hybrid mixers will never die. Because at this point in time, there is no way to deposit high mu materials onto semiconductors. At least not in a commercial way. I think people have done it at like the blue sky research level. And if I'm not mistaken, even DARPA wants this technology, but they're still pretty far out, I think, from any real commercialization. So that exotic mixer that I showed you, this one, that one right here, that's never going away. Because I can't do this in MMIC, and nobody can. But you can do everything else that doesn't require it. And that's what I'm going to show you now. So we took our knowledge of mixers, our knowledge of circuits, our knowledge of different balun designs, and we just put them onto 2D. And the first one we did is this one. It's a simple double balance mixer. The only thing I want to point out is that what's really cool about this process is that you can make 4 different mixers with the exact same design. Because all you're doing is changing the start wafer and changing the diode. When it comes to the linear specs, nothing changes. But when it comes to the nonlinear specs, which is defined as something called third order intercept, if you've heard of that, or single tone intermod, which is spurious products, those improve when you go to higher power diodes. And that's just what we're showing on this slide. But we went much further than that. We said, well, we can do the basic stuff now. Can we do the triple balanced exotic stuff? Can we do the MMIC equivalent of that crazy mixer, that spider's nest I showed you? And can we do even more exotic things like super broadband IQ mixers? The answer is we can. So these are just a couple of the examples. The upper right is a literal translation of the stuff that my dad was doing in the 70s, but on a MMIC platform. So it's kind of a cool, like, father-son duo thing. I asked him, what's the tricks? He would explain to me some of the problems. I'd go into simulation, 3D model everything, import the diodes, do a nonlinear analysis, fabricate. It worked beautifully. That mixer works, 5 to 30 gigahertz with 2 to 20 gigahertz IF. You have no benchmark for appreciating that. You just have to take my word for it. That's pretty cool. What's really novel about that, by the way, and it's not obvious, is triple balanced mixers have a special quality to them, which allows you to have what's called overlapping bandwidth. Double balanced mixers have like a physical separation of the band, so the IF band is never really that much overlapped with the RF and LO. But a triple balanced mixer allows you to overlap all 3, and that allows you to do these really wacky conversions, and that's really important in test and measurement. Test and measurement companies need to do these kind of weird band translations all the time because they're trying to improve the dynamic range of the entire receiver, for example. We also did this high linearity T3, we call it. So you see, we took the basic concept and we ported it over to 2D, but you notice we still left that ferrite balun there. That's the IF port. And we did that because customers didn't care about having ferrite on the L and the R, so that's what the chip was. And then we came off chip and did a hybrid assembly on the IF port. That's really hard to do. And we're probably one of the few companies in the world that probably would do it as a real product. We're very proud of that. We sell a lot of those now. It's been replacing the one on the left because it's more widely available and it's lower cost. Let's see, what else did we do? Oh, I didn't even mention this earlier. I think we're almost out of time. Yep.
On the last slide, do you still wrap the ferrites with wire, or is it just
Yep.
solder joints?
You can see it right here. So, right here, the ferrites. The ferrite. So that's a twisted pair. So it's 2 pieces of wire that are twisted around each other like a spiral. You take it and you feed it through. You can't see it, but there's actually 2 holes in that ferrite. It's called it's like a binoculars, something like that. And so you wrap it around a few times, and then you just solder to those 2 points. There, and then there and there. The way you actually manufacture it is you do that part first, then you clean it, and then you put it in an array, and you put it into a robotic machine that does automatic die pick and place. So you'll put like let's say a 250 some odd array, and there's a die holder, and it picks up a die, squirts down a little bit of silver epoxy, shoots the die down, and it does that 250 times. Then you go and cure it, and you bring it back to the machine, and then it comes in with it's gold wire bonding fixture, and it goes tap, 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 and you get all these little wire bonds. So you see 4 there, 2 there, 2 there. Every unit has that many wire bonds. I mean, that's a whole field unto itself, is how do you do that properly. I didn't mention this earlier, but I'll just leave you with this, because I think this might be the more fun, sexy thing about what we've done. So we took this design, which was already like our flagship design for high linearity product. We ported it over to the MMIC platform, and it worked really well. Then we thought, how much more juice can we squeeze out of this thing? How linear can you make it? And there's this trick that you can do in mixers where instead of having 1 diode, you actually stack 2 diodes. And when you stack 2 diodes, what do you think happens to the forward voltage? It doubles. Well, what do you think if you stack 4? Quadruples. Every time you double or go up by a factor of 2, you gain about 6 dB in linearity. And so we did that, and that's what this slide is showing you. So here's a single junction device. It was approximately that line. The double junction measured here. And then I'm not showing you the curve because we actually don't have the amplification yet to turn it on. It requires about 4 watts of LO drive. But we made a 4 stack diode right here. The forward voltage is about 2.4 volts, so it's about 4x what a standard junction would be. And we have customers, believe it or not, who need this kind of thing for really advanced research. That's pretty much it. This is just another version of a pretty exotic thing that hadn't been done yet. I'll leave you with this. If you want to appreciate the importance of semiconductor technology, the blue rectangle was the original size of the original part that we were selling. And we ended up getting it down to the orange size. And that's what the chip looks like. So it's like nearly a 100x improvement in area and commensurate improvement in cost. So that's it. Mixers in 50 minutes. So thank you.
Thank you, Dr. Markey, for that presentation on the amazing world of mixers and diodes and applications. If you'd like to talk to Chris, he's available right now.